A real-valued function f defined on R has the following property. For every positive number epsilon, there exists a positive number delta such that f of x minus 1 is greater than or equal to epsilon whenever x minus 1 is greater than or equal to delta. This property is equivalent to which of the following statements about f? Interesting. So they've taken the definition of they've taken exactly the definition of continuity at 1 for a function, but switched the inequalities, which of course will drastically alter alter how things work. So the the answer is certainly not A. So f is continuous at 1. That's definitely false. I mean, we could come up with counterexamples to that very easily. Almost any function that's not continuous at 1 would satisfy this, I bet. Okay, f is discontinuous at x equals 1. That's also going to be false. We can find continuous functions which satisfy this. In fact, let's let f of x equal x. Let's in fact let it equal, okay, let's just let f of x equal x. So we have something that looks like this. We have x equals 1. See, the thing is, it's a statement more not about values of x close to 1, but about values of x far away from 1. So let epsilon greater than 0 be fixed. I just have to choose delta. If I choose delta to equal epsilon, I think I'm done. Right? Then if the distance from here to here, like if x is farther away, then the function is farther away, right? So this is not the right answer, because we can find a continuous function which satisfies this. F is unbounded, option C. This might be correct. F is unbounded. Oh, so we're looking for equivalent, not we're looking for equivalent, not for implies. So options C, D, and E all look like possible candidates. I think it's D. I mean, it's basically the definition of although yeah, I usually like to go through these things one by one. Okay, let's give a counterexample here where f is unbounded. Let's let f be equal to x sine x. So it's unbounded. The problem is that it comes back to 0 infinitely often. Like for arbitrarily, I can find arbitrarily large values of x for where this is equal to 0. So there exists there exists a sequence xn which goes to infinity such that f of xn is equal to 0. So this means that f of xn minus 1 is equal to 1. And so this is saying that, if I let epsilon be equal to 2, then f of x minus 1, we want this to be greater than or equal to epsilon. If epsilon is equal to 2, this will not be satisfied for all values of x, which are very far away from 1, because there will always be some values of x where this holds. So this does not work. I'm going to skip to option E to show that this is also not correct. So option E says the integral from 0 to infinity of f of x in absolute value dx is equal to infinity. So for one thing, we're, an equivalent statement about f. Why are we integrating only on the positive values when the function's defined on the negative values? Like, how could there's something completely off with why we're considering only positive values of x. But let's let f of x be equal to 1 over x. Let's say 1 over, to avoid the problem at 0, let's go 1 over x plus 1. So this integral is infinity. But this function, it basically fails in a similar way to what we had up here. For very, very large values of x, the distance that this function is from 1 is 1, right? It's not exactly like this, but this function can't get that far away from the number 1. So this one fails as well. But C, F is, option D is the limit. This says that the limit as the absolute value of x approaches infinity of f of x is equal to infinity. So let's just write down first the definition of what it means for this. The definition of this is for all m greater than 0, there exists an n greater than 0 such that absolute value of x greater than n implies the absolute value of f is greater than m. It's not exactly what we have written here because these things are offset by, we have f of x minus 1 and x minus 1. But, absolute value of x approaches infinity. Is equivalent to x minus 1 approaches infinity. So don't really care so much. And similar for f of x, right? The absolute value of f of x approaches infinity is equivalent to the absolute value of f of x minus 1 approaches infinity. So this is the right answer. If we wanted to properly show that these two statements are equivalent, it would take a little bit more work. The thing that might be throwing a lot of people off that are used to these delta-epsilon type arguments is that typically when you're using, typically when you refer to epsilon and delta, you're talking about, you're worried about small differences or small numbers. And we often use large, capital letters to represent large numbers. But the way this is written, so it kind of could be confusing. But if you replace all the epsilons and deltas with m's and n's, then it should be a lot more familiar. Yeah, so anyway, D is correct. But if I have any kind of mistake, I'll be sure to let you know. Thanks for watching.